Good. So I'll talk a little bit about the ocean's role in the climate system, and I'll also discuss ocean acidification. And they are kind of separate issues. They're connected through CO2, and there may be some interactions there. And in fact, I guess one area where they're really connected is that the oceans are life in the ocean is being affected by acidification, but it's also being affected by warming. And there are other changes going on in the ocean as well. Oxygen is declining in many areas. And just sort of like with the forest fires, where you could have individual impacts of forest management, you could have individual impacts of climate, the sum of those, may not be equal to the actual combined effect of the two when they're acting together. And it's the same thing with ocean acidification. It's not acting alone, it's acting while the ocean is warming. And there have been a number of studies that looked at these so-called, they call them synergistic impacts. So in that way, these two areas are also related. All right, so let me get my laser pointer here. Okay, so yeah, so the way the ocean affects the climate system, I mean, it's really part of the climate system, but if you think the climate is sort of the atmosphere and the part we live in, the ocean affects the climate by exchanging heat and water with the atmosphere, and exchanging CO2 and even some other gases, like some sulfur gases that come out of the ocean naturally end up helping to facilitate formation of clouds, because you need particles for clouds to form on. And those particles, many of them, especially when you way out, in the distant part away from land, like in the southern hemisphere or the middle of the Pacific, you're really far from land. You don't have particles from land like dust and other things to supply the condensation sites, or nuclei as we call them, for clouds. So there's other really interesting ways that the ocean affects the climate, but I'm going to focus here mostly on heat and CO2. So this is a table from the Schmidt article that I suggested that you read. And the bottom line here, this table gives the mass of the atmosphere, the mass of the ocean, so-called unit heat capacity or specific heat capacity. And this is like if you have a kilogram of air or a kilogram of water, how much energy does it take to heat that kilogram of material by 1 degree Kelvin here, which is the same as 1 degree Celsius, by the way, or about 2 degrees Fahrenheit. And you can see that the ocean, it takes more energy to heat a kilogram of water a certain amount than it does the air. So that's one factor, but it's really the mass of the ocean that is the big difference between with the atmosphere. But it's the product of these two, the mass and the specific heat, so-called total heat capacity, that is important here. And this thing is about 1,000 times bigger for the ocean than it is for the atmosphere. So if you wanted to heat the ocean 1 degree C or 2 degrees Fahrenheit, it would take 1,000 times more energy than it would to heat the whole atmosphere, that amount. So there's an enormous sort of capacity for the ocean to absorb heat without it warming up very much. So it's really a good thing, and it's sort of our friend when in many ways when it comes to climate change. So that heat capacity, what that means is that as heat is being added to the surface of the earth, both land and ocean, during the summer, the ocean is going to warm up a lot less than the land. And so climates that are people that live near the coast or particularly downwind of the ocean, like in California here, you got a very moderate climate here. So what's being shown here is the annual temperature range. That is the temperature your hottest month minus the temperature your coldest month. It's like how extreme seasonally is your climate. And these red areas are really extreme. and the blue areas are really moderate. So you can see it's over land, particularly when the air is taking a long time to get there from the ocean. The air at mid-latitudes travels from the west to the east. So this land here the air here hasn't seen much, hasn't seen the ocean in quite a while. And so this is a very continental climate, extreme temperature range. We see similar things in the central part of the United States and Canada, whereas, and even in the southern hemisphere, Australia's got a bigger range than over the ocean. So the ocean has this sort of moderating effect seasonally on climate. These maritime climates are much more moderate than continental climates. So that's one effect. Let me just see here. I'm not see if there's any questions in the chat. I'm not seeing the chat here, but if they come up, just maybe you can let me know, John or Isaiah. So there's another way that the ocean moderates the climate, and that is it takes in heat at low latitudes from the atmosphere, and it transports it poleward in both hemispheres. And then it releases that heat back to the atmosphere at high latitudes. And that's sort of, part of that is shown in this map, which is a heat flux map. And so the red areas are where heat is entering the ocean from the atmosphere. So you can see these red areas, not exclusively, but mostly they're in the tropics. And then the blue areas, you see this big area here over the Gulf Stream, and there's another similar current here. The blue areas, and you see they're mostly at higher latitudes, is where heat is coming out of the ocean. So so the ocean is giving heat to the atmosphere at higher latitudes. And we could quantify that by this graph here that's also from the Schmidt article that shows the transport of heat in petawatts. This is 10 to the 15 petawatts. It's a lot of energy. And basically positive values here. Here's the total heat transport by, it's not only the ocean, but the atmosphere does it, by the ocean atmosphere system. You can see these values are positive in the northern hemisphere. And the convention is if it's northward, it's positive. And if it's negative, if it's southward, it's negative. So you can see that just looking at the black curve and looking just at the total atmosphere ocean system, because the atmosphere does the same thing too. It receives heat from space, sunlight from space at low latitudes, and then it releases that energy at high latitudes in the form of infrared radiation. It's radiation that you can't see. So the two of them do it, both the ocean here in blue and the atmosphere in red. You see all these positive values in the north, negative values in the south. They're transporting heat poleward. So what that does is that cools off the tropics, which are already hot, and warms up the poles, which are cold. So that's another moderating influence of the ocean and the atmosphere, by the way, on the climate. You see the atmosphere is actually in some ways more effective transporter of heat, but the ocean plays a very, very important role in this. Okay, so you can see a picture here, maybe it's a little more vivid here. This is a satellite image, one of these NASA satellite images of ocean temperature. It's like an infrared camera. It's like one of those night goggle vision kind of camera, which works on heat. And here you can see a picture of the ocean temperature. And, these redder colors are, of course, warmer. And you can see the Gulf Stream here. It's a very intense current, that hugs the east coast of the United States, and it takes this warm tropical water and carries it northward. It's very dynamic. You can see all these meanders and stuff. It's really a beautiful thing. So that's one way in which the ocean transports this heat poleward. And you can see here's another interesting map. It's kind of another weird temperature map. It's not the temperature. What it is, it's the difference. It's the actual temperature minus the average temperature for a given latitude. Okay, so look here. This is just to orient you. Here's North America. This is like the Northern Hemisphere. Here's North America, here's Europe, here, this is the Atlantic Ocean. And you can see here, just west of, east of Greenland, the temperature of the air is like, 10 or 12 degrees Celsius warmer than average for that latitude. Okay, and the reason why it's warmer is because the ocean is carrying heat poleward with the Gulf Stream and other currents. So that's why Northern Europe has this relatively moderate climate, say, compared to, Northern Canada. So like if you're in Scotland, you're pretty far north actually, but it's quite, the climate is quite moderate, so you see that effect here, the temperature here in Scotland compared to, central Canada. They're at the same latitude, but Scotland and England are much warmer. So that's another moderating effect. So this massive heat capacity of the ocean also means that all the additional heat from global warming, which you've been learning about, is going into the ocean. And this is a little bit dated graph now, but the point is still the same, that about 90% of the heat from global warming is going into the ocean. The rest of it is going into land, the atmosphere, and heating some ice. And that's because of this enormous heat capacity of the ocean, but also because it can mix and exchange with the atmosphere, which sort of land really can't do, and ice really can't do. It's, because it's so static. So this was, last time I taught, this article had just gave the lecture. This article had just come out, and it was kind of exciting, and it showed that the ocean is actually heating up more than we thought. And we've been monitoring the ocean much more effectively. We have these basically robots that are patrolling the ocean. They look like poster tubes. They're about this big, and they go up and down the top few kilometers of the ocean every 10 days. And there's about 3,000 to 4,000 of these out in the ocean now, all over the ocean, and they measure temperature. So, we're seeing like almost in real time how the ocean is warming up. So it's really spectacular technology, international effort. Really, it's one of these, beautiful international collaborations that is giving us all this really useful information. And these data and other approaches show that the ocean's been warming up even more than we thought. All right, and that warming of the ocean is causing the ocean to expand, because water expands when it's heated. And of course, glaciers on land are melting and running off into the ocean. That's increasing the mass of the ocean. That's causing the ocean to rise. And you can see that, we talk about sea level rise, but there's actually sea level acceleration, because the rate of increase now is greater than it's been throughout the 20th century. And that's leading to, more frequent flooding in coastal areas. These so-called sunny day floods are happening more and more. I think I'm going to take a pause there. Are there any questions about sort of the heat part of this discussion? How the oceans. Well, maybe this is a good time to talk about hurricanes, because that was a question, and there's a question about the climate change and hurricanes. And basically hurricanes, the fuel for hurricanes is water vapor. And when that water vapor condenses in the atmosphere, heat is released and it makes the hurricane more powerful. So the more water vapor you have in the atmosphere, we expect hurricanes to be more powerful. So, and we're seeing that in the data now. We're seeing that that hurricanes, the strongest hurricanes, are getting stronger. Another factor is that the flooding due to hurricanes is going up because, for two reasons. Sea level is higher, so the storm surge that's created by a hurricane is more damaging because you have basically more water to push on shore. But then also the atmosphere is moister, right? Because of the ocean's warmer, more evaporation. And that means when the hurricane removes that moisture from the atmosphere in the form of precipitation, it's got more to work with. So you get more flooding. And the studies have shown that the hurricanes that we're getting now are producing more precipitation than they would have in the absence of global warming. So there's a few. Then there's even a third effect now that, or fourth, am I up to fourth? The fourth effect of climate change on hurricanes, and maybe you've read about this, is that hurricanes are kind of stalling more. They're not moving, they're not translating as quickly as they used to. And this is more bleeding edge science, but there's a few studies that have shown that there's a variety of reasons, we could get into it, but hurricanes are moving more slowly now as a result of climate change. And that means they'll dump more precipitation in a particular place. And of course that leads to worse flooding. Okay, I'll move on, talk about carbon here. And this is a table, I think, from Schmidt as well. And it's showing that the ocean, it's not only got a lot of sort of heat kind of capacity, but it's a big carbon reservoir. And it's the biggest out of all the reservoirs listed here. And you could, even fossil fuels. And it's really it's the biggest reservoir that actively exchanges with the atmosphere. You could add rock into this too. And I think if you take all the carbon in the solid earth, it's massive, but it's not exchanging with the atmosphere. And so that's the sort of main point that one can make with this table. We'll get more into these numbers shortly. So you saw this slide from Dr. Sentesy, and it shows that CO2 gets in the ocean, it dissolves in the ocean. Gases can dissolve. So, gases can be bubbles in liquid, but it can also just completely dissolve. And when it does dissolve in the ocean, it reacts with water, liquid water, and it forms carbonic acid. And it's actually a two-way reaction. It's a so-called equilibrium reaction. It happens very quickly. There's more reactions that occur. That carbonic acid will break up and form hydrogen ion, carbonate ion, and then that reaction will go further and make more hydrogen ion and so-called bicarbonate ion. And this is why the ocean can hold so much carbon, because actually most of it is not in this form. Only like 0.5% is as CO2, about 10% is as carbonate ion, and about 90% bicarbonate ion. That's what makes the ocean such a massive reservoir of carbon, and has this great ability to absorb carbon dioxide from the atmosphere. So I showed you a heat flux map before. Now I'm showing you a CO2 flux map. This shows where CO2 is going in and out of the ocean. So the red areas are where CO2 is coming out, and the purple areas are where CO2 is going in, and it almost balances. But there's enough of an imbalance when you average over this whole surface. What you see is that CO2 is going into the ocean. This is one way we know the ocean is absorbing carbon dioxide. We can also look at it with time, and we can see the CO2 levels in the ocean going up with time. That's another way. And this shows, Mark showed a plot like this. This is basically the same thing. It's just a different color scheme showing where human-produced CO2 has gone into the ocean. And these are quite sophisticated techniques to make these maps, and I can't really explain how they're done. It's quite complicated. It's a whole other lecture. But what it shows is that the ocean is taking up a lot of carbon dioxide in the northern hemisphere, particularly in the North Atlantic. And the reason why is that this is where a lot of water is sinking into the deep ocean. So the ocean can carry carbon into the deep ocean very, very quickly here. And there's other places where waters are sinking, and that's in the southern hemisphere. Okay, so the ocean has played a tremendous role in absorbing carbon dioxide, and that's shown in this graphic from the Global Carbon Project, which is another international collaboration with like very little funding. It's just sort of done like almost on a shoestring budget because scientists just thought this was important to do. And it comes up with a carbon budget every year for the globe. And this shows what's happened since 1850. We were at about 286 parts per million in 1850. Coal burning and oil burning and gas burning, all fossil fuels, as well as some cement production, would have caused, through 2018, atmospheric CO2 to go up to almost 500 parts per billion. Land use, mostly deforestation, would have caused it up to go even further, up to almost 600 parts per million. Of course, we're at 400, a little above 400 parts per million now. And that's because the land itself has also absorbed carbon dioxide, and for a variety of reasons. But also the ocean has absorbed carbon dioxide as well. And so that's why we're down here instead of up here. We've got these land and ocean sinks. And you can see the land actually cancels out. So really the ocean is the main long-term permanent sink. And that's why it's so important with regard to the carbon budget of the atmosphere. So here's the modern day carbon budget put together by the Global Carbon Project. And you can see this is in gigatons of carbon dioxide, which is it's different than gigatons of carbon, but the main point is that most of the inputs are from fossil fuels. There's some from land use. About 40% of that has accumulated in the atmosphere, and the rest is roughly evenly split between the land and the ocean. Now, let's talk about ocean acidification. So we saw this figure before, and here I've highlighted some of the products of this dissociation of carbonic acid here, right? So one of the dissociation products is the hydrogen ion. The hydrogen ion is what gives the ocean its acidity. So you can see that when we add CO2 to the atmosphere, it goes into the ocean, we're going to get more hydrogen ion. And for two reasons, right? For this step here, and then this step over here. So that's ocean acidification, basically. And we've actually measured this. This is shown here. This is the pH, right? Which is a familiar measurement of the acidity. Now pH, it's got this weird kind of scale. You got to take the log of the hydrogen ion concentration and then put a minus sign in front of it. So, and the hydrogen ion concentration has to be in molar units for the chemists out there. Anyway, the main point is that as the pH goes down, that means the hydrogen ion concentration is going up. You're getting more acidic. And we've been monitoring the pH in the ocean at several of these stations in the middle of the ocean, right? Bermuda, Hawaii, Canary Islands, and you can see the pH is going down everywhere. So this really confirms our theory about ocean acidification. It's going down exactly how we would expect it, the pH. So that's ocean acidification. And really, what ocean is, it's not so much the organisms don't care so much about the hydrogen ion. Really what happens is, as Mark pointed out in this slide, is the carbonic acid combines with carbonate ion and actually consumes the carbonate ion. So this is a weird thing about the carbonate chemistry. Even though it looks like carbonate ion is going up here, the reaction is the chemistry is a little bit more complicated. And the truth is that this ends up reacting with this and forming bicarbonate ion. So why does that matter? Well, I don't think I wrote the equation here, but to form calcium carbonate, that's CaCO3, you need this carbonate ion. And that's going down with time. And so that's going to give organisms that need to make their shells, and there's a whole variety of calcareous organisms in the sea. And this kind of gets to the question about land impacts of ocean acidification. Oysters, for example, right? We eat oysters. Well, they're affected by ocean acidification. And oyster farmers are really concerned about this. You know, how big is the impact so far? It's hard to say. I don't know if it's having a dramatic impact now, but there's concern that as the ocean acidifies, you know, the seafood that we draw from the ocean in the form of oysters and other calcareous organisms, clams, even fish, right? Their skeletons are calcium based. You know, we may see some negative effects of that in the future. So that's the concern about that. Now this is the same location now showing the carbonate ion concentration, right? This is the stuff that the corals, clams, all kinds of fish, they need this to make their calcium carbonate structure. And you can see this is going down everywhere. So this is the concern about ocean acidification. And there's planktonic organisms as well that serve as the base of the food chain. So these are microscopic organisms like coccolithophorids. They're very important. There's forams, foraminifera, are important microscopic animals that serve as the base of the food chain. They're affected by ocean acidification. So that's the concern. So I can summarize now. We'll go back to the ocean as a moderator of climate, and it does it in a couple of ways, right? The ocean makes summers cooler and winters warmer. It transports heat poleward, so it makes the tropical regions cooler and polar regions warmer than they would otherwise be. And it moderates the climate by not making global warming so bad, because if the ocean wasn't absorbing all that heat, it would be going into the atmosphere. And that's another way to scale it. We scaled it with 50%, but if you look in terms of heat, that's a 9-to-1 ratio. So you might be inclined to argue if the ocean weren't there, we would see 9 times as much warming. I don't think anyone's done the sort of calculation. How much global warming would we have without the ocean? It's really interesting. So that's one way it moderates the climate, through heat, but it also moderates the climate by absorbing carbon dioxide. So it wasn't absorbing all this CO2, it would be in the atmosphere and creating warming. And I do like to make this point that the ocean's the only long-term sink of anthropogenic CO2. And then finally, just some summary points about ocean acidification. The ocean's becoming more acidic. It's becoming more acidic because it's absorbing CO2 and forming carbonic acid. And then carbonate ions gets consumed in the process, and those carbonate ions are needed for calcifying organisms to form their shells. So that's the negative impact of one of the negative impacts of ocean acidification. So I'll stop there. I'm a good teacher.
Thank you so much, Ray. I really appreciate it. Silent claps from everybody, yeah. Visual claps from everybody.
Thanks.